Okay, and so that is an extension of independence. Okay, so originally we consider independence of two random variables, but now we can extend the notion of independence to two groups of random variables. And then furthermore, we can have, say, k groups of random variables, right? And these k groups of random variables are independent. Okay, you can write down the definition immediately by a direct extension of this definition here. All right, and so now as the remark I made here for n independent random variables, we can have similar result for two independent collections of random variables. Okay, so remark. All right. So for proposition 6.2.a, all right, for propositions can be 6.2.c can be extended to two independent collections of random variables. Okay, so first of all, x1, x2, up to xn. This collection is independent of maybe I will say here two collections x1, x2 up to xn, and y1, y2 up to yn. Two collections of random variables are independent. If and only if the joint CDF of the n plus m random variables, okay, so this one is the joint CDF of n plus m random variables x1 up to xn and y1 up to ym is equal to the joint CDF of xi of x random variables times the joint CDF of y random variables. Okay, so this is the joint CDF of n random variables x1, x2 up to xn the joint CDF of m random variables, y1, y2, up to ym. Okay. So this is the even-only condition. Okay. So from this result, you see it's not difficult, right, to identify two collections of random variables are independent. Okay, just to observe whether you can have such an identity. Okay, so for all right, you can have a second one. So two collections x1, x2, up to xn, and y1, y2, up to ym of discrete random variables are independent, right? If and only if they are joint PMF, x1, x2, up to xn, y1, y2, up to ym is equal to p x1, x2, up to xn, x1, x2, up to xn, times the joint PMF of y1, y2, up to ym. Okay. And the third one, two collection next one, x2 up to xn, and y1, y2 up to ym of jointly, absolutely continuous random variables with a joint PDF f x1, x2 up to xn, y1, y2 up to ym. So these m plus m random variables are jointly, absolutely continuous with a joint PDF, this one. And these two collections are independent. If and only if they are joint PDF, their joint PDF can be written as the product of the joint PDF of xi's times the joint PDF of yj's. Okay, for almost all x1, x2 up to xn, and y1, y2 up to ym. Okay. So the idea can be copied, even though we just developed the theory for two random variables. But the idea that everything can be extended to like a finite number of random variables, or to be independent, or an infinite collection of random variables are independent, or two collections of random variables are independent to each other. Okay, so this is we have the tools, okay, to identify which and which are independent to each other. Okay, okay. So we can manage that kind of complexity, right? Even though we started from only two random variables, but the concept can be extended to very general cases. Okay, and there are some important factors I think I have to raise up. Okay, before we leave the classroom. By the way, any questions? Yes, please. Yes, we can extend them. No problem for n random variable and for two collections. Yeah, we still can do that. Yeah, no problem, because these two are some corollary of property 2 and 3, right? So you can apply different properties. For absolute continuous case, you have to apply the third one, and for discrete random variable, you have to apply the second property. So both of them can be extended, of course, without any problem. Yeah, good question. Other questions? Because I hope that after today's class, in your career, when you encounter problem about independence of random variables, you have already have every tool here provided in this classroom. Okay? Other questions? All right, so I think I have 5 points to make. So I'm sorry, I have to borrow sometimes from you. All right, and so x1, x2, up to xn are independent random variables, right? Now you can utilize the concept introduced right now. So we can rephrase the statement here, saying that if and only if x2 is independent of x1 first, and x3 is independent of the collection x1, x2. All right? And then x4 is independent of x1, x2, x3. And you can continue. All right, and finally, xn is independent of the collection x1, x2 up to xn minus 1. Okay, so you can use the concept of independence of two collections. Okay, because a single random variable can be considered as a collection with only one member, right? So x1 and x2 can be represent two collections, and they are independent. So x2 is independent of x1. Then x3 is independent of x1 and x2 together. Okay? And then together. And you can prove that, all right, as an exercise. Okay? If you can do the proof, that will indicate that you understand the concept I introduced today. All right, so it's a benchmark for you. All right, try to prove it. Okay, I recommend you to use property 1. Okay, will be enough for you. All right, now recall. As we know, a function, a data processing of a random variable will give you another random variable if the data processing function is, for example, is piecewise continuous, right? So recall in chapter 5, proposition. (5.2.b) says that if x is a random variable and g is a piecewise continuous real value function, on the real line, then y defined to be g of x is a random variable too, right? So we say that if the signal processing function g is piecewise continuous, then after the signal data processing, okay, g of x, this new function on the sample space, is again a random variable. Right? Proposition 5.2.b can be extended for data processing on several random variables. Okay? So that this is our random experiment. Okay, so you have an outcome. And the outcome will go through several measurement devices. X1, measurement devices, Xn, so X1 omega, Xn omega. And they will go through, so the data, the measurement data will be go through the same data processing. So we have data processor, okay? And give us G of okay? And we define this to be y of omega. Okay. So now, so a question is y random variables. Now, a real valued function g of x1, x2, up to xn on Rn, okay, on the n-dimensional Euclidean space Rn is called piecewise, okay, continuous. Okay. It's easy to define piecewise continuous function on the real line, okay, if the domain is the real line. But if the domain is n-dimensional Euclidean space, so how do we define piecewise continuous? Okay, so such a real value function is called piecewise continuous if it is itself continuous in Rn, that is fine, right? Or there exists, all right, a piecewise smooth hyper surface which partitions the space Rn into countably many open regions UI such that G is continuous on each UI. All right, let me take a picture to illustrate the idea. All right, so n equal to 2. So now we consider a probability function on two variables, okay, x and y. Okay, now we call it piecewise continuous if the function itself is continuous over the plane, that's fine. Okay, there are so many functions like that. For example, continuous. For example, linear function, right? For example, linear function. For example, linear function a1 0, right? So AIs are constant linear function. So linear function is continuous in the n dimension. But some function may not be such nice function, okay? So you may have a piecewise smooth hypersurface which partition the space, which partition the plane. So for example, you may have a surface okay, like this one. So this is a surface. So it's a piecewise smooth hypersurface. Okay. A hypersurface is a surface with dimension n minus 1. So for n equal to 2, n minus 1 is 1. So a hypersurface for the plane would be a curve. Okay, a curve, because a curve is one-dimensional object. And it's piecewise because that at this point it's not so smooth. Why? Because this point you can go this way or that way. Okay, so there are two directions. All right, so this hypersurface is not smooth at this point, but we can exclude that point, right? So you can see at least you can this part. All right, so this part is smooth, and the other part is also smooth. The red part is also smooth. Okay, it's also smooth. So it's piecewise because we can into piece by, so you can use some points. So point is zero dimensional, right? So to divide the hypersurface into several parts, and each part is smooth. Smooth means that you can have a coordinate function which is infinitely differentiable. Okay, so this course is very smooth, so it's infinitely differentiable. Okay. All right, and so now the R2 can be partitioned. So here R2. So the whole plane can be partitioned into three pieces. One piece, two pieces, and the first piece, second piece, and the third piece here. Okay. Okay. So now I will write here. So without the boundary, right? So this part the green part. All right, so this an open region. Okay, open region, and also this part. This is the second open region. And the outside is also an open region. Okay. So now this hypersurface, this piecewise smooth hypersurface will partition the plane into countable many. Here we just have 3. All right, 3 open regions here. All right. And the region, when we said a region means a connected component. So when we say this is a region, because that any 2 points can be connected by line segment for open regions. Okay, so in topology, okay, so they must be connected together. Okay, at this point. All right, and then the function g. So this would be u1, and then this is u2, and here you have u3. Okay, and over each ui, the g is continuous. So g is continuous over this open region u1. And G is continuous over this open region U2, and G is continuous over the outside, the open region U3. Okay. In this case, then G is called piecewise continuous. Okay. Any questions? All right. So maybe I will define some terminologies here. Region. What is a region? Okay. An open set in Rn is called connected. Okay, an open set is called connected if for all any two distinct point P and Q in U, they can be connected by line segment. For example, in R2, so in R2, an open set, say a ball here, okay, a disk, open disk here, and if you have 2 points, P and Q, you can connect them by, for example, by this line segment. I think connected by not, I think, not only a nice, I should say poly by a series of line segment. Okay, so that is good. Another case is that okay, this region, this is connected. This is also connected. Why? Because that if I have P here and I have Q here, then you can go in this way. Okay, so it connected by 3 line segments. Okay, so can be connected by 3 line segments. This is it's a convex set, so that's only 1 segment will be enough. But this is not convex, so we may need more than 1 line segment to connect them. Okay, so by a series of 9 segments here. But if all right, so this is U1, this is U2. But if U is equal to U1 union U3, then U is not connected. Why? Because that if I have a point here, another point is here, then you cannot have a non-segment to connect them. By a series line segment in U. I forgot to put, okay? So please add in U, because line segment should be contained in U. Okay, so in the open region, so now I will say that an open region in Rn is just equal to a connected open set in Rn. Okay, so an open region is just a connected open set. Okay. So it's a convection. So this is a connected open set. This is a connected open set. Also, this is connected. Because if you have a point here, if you have a point, say here, and a point Q here, how can you connect them? Well, you can go this way and this way and go. All right, so by using 3 line segments in U3, P and Q can be connected. Okay, so U3 is also a region, an open region. Okay. Okay. All right. So now, this is a definition of piecewise continuous functions on Rn. Okay. So if the function g itself is continuous, that's fine. But in many situations, it's not continuous over all the n-dimensional Euclidean space. But you can still partition the n-dimensional Euclidean space by using a piecewise smooth hypersurface. Okay. For example, in 3 dimensions, you may use a ball. Okay, a ball. All right, the surface of a ball to divide the 3-dimensional space into 2 regions. One region is inside the ball, the other is outside the ball. Okay, and the surface of the ball itself is already smoothed surface. Okay, the whole surface is already smoothed. Okay, anyway, so all right. So this category, this kind of functions will be general enough for you to use. And so now we are able to write down the result. Okay, so I will summarize in the proposition 6.2.d. If x1, x2, up to xn are random variables, and g of x1, x2, up to xn is a piecewise continuous real valued functions on Rn, then g of x1, x2, up to xn. So this composition is also a random variable. Okay. So it's a general proposition. And the last proposition, 6.2.e. So let x1, x2, up to xn, and y1, y2, up to ym be 2 independent collections of random variables. Assume g of x1, x2 up to xn. So the measurement result of the x random variable will be put into the data processing function g, okay? And the y measurement will be put into another data processing function H. And assume both these two are two piecewise continuous real valued functions on Rn and Rm respectively. Okay, then G of x1, x2 up to xn, these random variables, and H of y1, y2 up to ym, okay, another random variables are independent random variables. Okay. So if we have two independent collections of random variables, and each collection has been data processed separately, okay, then the result, these two results, right, will be independent random variables. Okay. And so the proof will be omitted. Okay. But I'd like you to use them, both of them, okay? Because they are very useful, okay? As you will see, both of them are very useful theorems, okay? Because that you will encounter a lot of data processing functions in practice, okay? And those data processing functions, G, or H, are piecewise continuous. Okay, and so this theorem makes sure that after the data processing, the result is also a random variable again. Okay, and the last proposition gives you that if the original data form two groups of independent random variables, okay, so you have two independent groups, right? Inside one group, they may be dependent on each other, but as a group, this group is independent of the other group. And so after the data processing on the first group and after another data processing on the second group, then these two process the output, the result will be statistically independent. Okay? Any questions? Okay? So if no questions, I'll stop here.